Might as well.
Might as well. Good morning. Happy Friday. Um, all right. So we didn't meet on Wednesday, of course, so it was a little while ago. Just a quick review. Oh, I should say, so I haven't heard from Shaun. I don't know if he'll be back next week. So unless you hear anything, we'll just keep meeting here. So, oh, and what I'll do is, so you don't have to rush to mute there. But I have to change it in my settings every time. I'm sure I can change it overall, but there. Okay, so unless you hear otherwise, we will keep meeting here next week in Zoom. Next week. Okay, so because I haven't heard anything, I don't know. Happy to keep meeting with you guys. So we'll see what the deal is. Okay. I don't know anything. I know Shaun canceled one of your tests. He said we were going to keep another one. So I don't know anything about that. If you have questions about that, then message Shaun. I'm just here to blab at you. Okay, so for a review, we talked about combining functions. So combining functions, we can do it either algebraically, so things like f plus g of x, but what we said was that's just the same as f of x plus g of x, right? Same thing with f minus g of x is f of x minus g of x, right? So we can make this new function called f minus g of x, but really it's just combining these functions by subtracting them, right? And so we are combining functions to create new functions, but algebraically it's not really that surprising, right? So we can have, just so we have the full list here, f times g of x is just f of x times g of x. And of course, f divided by g of x is f of x divided by g of x. All of these, right? So f of x has a domain and g of x has a domain. It's important to talk about the domain of functions, right? Because we need to make sure, so the domain is all the allowable inputs. So we need to make sure that what we're putting into these functions is allowed, right? And so for the domain, we have to remember we can't divide by 0, right? So any input, so any x that makes us divide by 0, we have to pull it out of the domain, and any square root of a negative, we have to pull that out of the domain. So we can't divide by 0. And we can't take the root, the even root of a negative. And I don't know, flipping through Shaun's notes, I feel like he's already brought up the log. And so, but I don't know if he's incorporated into our kind of domain spiel yet. We can't take the log of a negative or a 0. I'll leave it off for now because we haven't gotten to logs yet. So even though I've seen it in his notes, I'm going to leave it out for now. So to find the domain of these guys, all these algebraically combined functions, right, what we do is we just find the overlap of the domain of f and the domain of g. So let's see here. The domain is the overlap. In fact, I'm going to scooch this over a bit. Is the overlap of the domain of, and I made this too, oh, of course. I'm going to bump this down a bit. Oh, hi, Beezers. The dog just got in, and she's so excited. Okay, so, and make this nicer maybe. There. So the domain is the overlap of the domain of f of x, of the domain of f of x, let's call it A, and the domain of g of x, right, call it B, right? So the overall domain is A and B. Let's see here. With the additional condition here when we're dividing, right? So here we have A and B, so it's just the overlap of f and g, the domains of f and g, and here for f divided by g of x, the domain is A and B, and g of x can't be equal to 0, right? Because we're dividing by g of x, so we need to add the condition that we can't divide by 0. We also talked about, so this is algebraically, combining functions algebraically. We can combine functions through combinations. Compositions. Compositions, I mean, technically correct. Compositions are things like f composed with g of x, right? And so here, this kind of circle is composed with so f composed with g of x just means in place of x in f of x, you're going to put in g of x. So you're going to stuff a function into the function. So how we can write this is f of g of x. So what I usually end up doing is instead of reading it properly, f composed with g of x, I just read it as f of g of x. Right, because then that reminds me that I'm stuffing g of x into f, okay? And so here, and we can compose all kinds of different functions, right? Even more than 2 functions, we can stuff them into each other, and you just kind of stuff them in from the right. And we'll see an example in just a little bit. But for the domain, what's tricky is, okay, so f of x and g of x each have a domain, right? But g of x is going into f of x. So what you have to do is you have to keep an eye on the domain of g of x, right? Because whatever you're putting into the function has to satisfy g of x, right? But also the outputs of g of x have to satisfy the inputs of f of x. So it's a little bit trickier to find the domain of a composition. We need to satisfy the domain of g of x, right? In the case that g of x is the one that's going into f of x, we need to satisfy the domain of g of x, and the outputs of g of x must satisfy the domain of f of x. Must satisfy the domain of f of x. Oops. So that can be a little bit tricky, but for the most part, what happens is we can just look at the final function and look at the domain. That's not always the case, but for the most part, for what we're doing, we can just look at the final output. I might need a little bit more room than that. Most of the time, we can simply examine the final function. Simply examine the final function. So let's do some examples here. And I'll bump this up and call it the end of the review. Bump it up. There. Yeah. So, for example, let's say we have, let f of x be the root of x minus 2, and g of x is going to be 2x minus 4. The first thing I need you to do is just look and figure out what the domains of each of these things are. It's just good to have a good handle on what these domains are. Even if we don't use them for a particular composition, it's just good to have an idea. So here we've got a square root, so we have this kind of mental thing, mental stopper that says, oh, a square root, I can't take the square root of a negative. And so I need to make sure that x minus 2 is greater than or equal to 0. Right, so here, the domain is that x minus 2 has to be greater than or equal to 0. So what I can do is I can treat the inequality as if it's an equal sign as long as I'm not multiplying or dividing by a negative. Right? If I'm multiplying or dividing by negative, I have to switch the sign, but then I can just do my math like I want to. So in this case, right, to move this 2 over, minus 2, I'm going to add 2 to both sides. So I'm not multiplying by negative. So x has to be greater than or equal to 2. You can check it out, right? 2 minus 2 is 0. Okay, that's fine. I can take the square root of 0. 3 minus 2, safe, right? Square root of 1, it exists. And so it seems reasonable. Here, if we're looking at 2x minus 4, right, there are no restrictions here. 2x minus 4, I can plug in any value of x and I'll be able to compute what g of x is, no problem, right? As soon as you see something like this, a polynomial of sorts, right, just a bunch of x's on the same line, so no division, no logs, no square roots, then the domain is going to be all real numbers. So here, the domain is that x is in the set of real numbers, right? Or if you want to think about it from negative infinity to positive infinity, that's fine too, right? That's the set of real numbers. So knowing that, how about we do some compositions? So first, let's find f of g of x. Okay. Part E, let's do g of f of x. Okay, very important that we see that these two things are never or very rarely going to be the same thing, right? Unless they're kind of the same functions. Would be the only scenario. So these are always going to be different. So that's important. And let's also find f of x and and also g of x. Why not? Okay. Find the following and their domains. Okay. So if we start with f of g of x, f of g of x is going to be, so f composed with g of x. So what I like to do is I like to write out f of x, but replacing x with g of x. And if you prefer, you can just stuff in g of x right away, but I find that very confusing sometimes. And so f of g of x is the root of g of x minus 2, right? Notice that here we're just replace x, oops, replace x with g of x, because that's what I did here, right? I replaced x with g of x in f of x. Okay, so now I've got the root of g of x minus 2. Being careful that g of x stays as one thing, right? I can replace it with 2x minus 4. Not that important here, 2x minus 4 minus 2 is safe. But what if this was switched around, right? What if it was 2 minus g of x? Then you would have to pull this negative inside, right? So that's why I say you have to be careful and treat g of x as one thing. So here, we've got the root, and I like to put brackets around just to play it safe, 2x minus 4 minus 2. Okay, so I've got the root of 2x minus 4 minus 2, putting me at 2x minus 6. So for the domain, okay, so remember what we had was, okay, g of x is going into f of x. So g of x has a domain of all real numbers, so there's no restrictions there. Okay? What has to happen next is that g of x, the outputs of g of x have to satisfy the domain of f of x. And so g of x is replacing x here. So g of x minus 2 has to be greater than or equal to 2, okay? Which we did the work already, and we found that g of x has to be greater than or equal to 2. So we could start and say, okay, well, g of x has to be greater than or equal to 2. All right, fine. Or in this case, right, that's going to be the same as 2x minus 6 has to be greater than or equal to 0. So, but just for consistency, right, let's do the domain here. Domain, well, g of x has domain x in the set of real numbers, right? So no restrictions there. So there are no restrictions on g of x, okay? And then we need to make sure that g of x, right, the domain of f of x has domain x has to be greater than or equal to 2. Therefore, g of x must be greater than or equal to 2, right? Because I'm putting g of x into f of x. So if g of x has to be greater than or equal to 2, I got 2x minus 4. So 2x minus 4 has to be greater than or equal to 2. I can add 4 to both sides, right? Moving that 4 over. And then as long as I'm not multiplying or dividing by a negative, we're safe. So we get 2x has to be greater than 6, greater than or equal to 6. So x has to be greater than or equal to 3. Okay. Then we combine these domains, right? So no restrictions on g of x, so that's fine. So the overall domain is going to be x has to be greater than or equal to 3. This is our overall domain. Oops. All right, g of f of x. Okay, so now I'm putting f of x in as x into g of x. Ugh. But here we go. G of f of x. Well, g of x is 2x, but I'm going to replace x with f of x minus 4. Then I can replace f of x with f of x minus 2, so the root of x minus 2, and then minus 4. Okay. Here, I have restrictions on f of x, right? X has to be greater than or equal to 2, but no restrictions on g, so I'm allowed to put in anything that I want. And so the domain here, and there's nothing I can do to simplify this, so I'm just going to leave it. The domain here, f of x has domain x greater than or equal to 2, and g of x has domain x in the set of real numbers. So overall, the domain is the overlap of these, so x has to be greater than or equal to 2. Okay. Next one we wanted to do was f of x. F of x is the root of f of x minus 2, right? So just plugging in f of x wherever I see an x, and then replacing it again. So now I've got the root of x minus 2 and then minus 2. Notice here, right, I want to emphasize that this x minus 2, the square root, ends here. So what I'm going to do is I'm going to draw a little hook there just to remind myself that this square root ends over the x minus 2, and then this minus 2 is just under this square root. In fact, I can do the same thing over here. Just to emphasize where these roots end, right? You don't want to be sloppy about that kind of stuff. So here, okay, we've got the domain of f of x is that x has to be greater than or equal to 2. But then I'm plugging in f of x in for x. So now I have to also make sure, I'll use a different color here, the domain is, okay, so f of x has domain x has to be greater than or equal to 2, right? And f of x, okay, has domain f of x has to be greater than or equal to 2, right? Which means that, okay, the root of x minus 2 has to be greater than or equal to 2. So now I can square both sides to get x minus 2 is greater than or equal to 2 squared. Oops, 2 squared. So x minus 2 is greater than or equal to 4. And then I can add 2 to both sides. So I get x must be greater than or equal to 6. Okay. The overlap of this, so if the first one is saying, uh-oh, my screen sharing ended. I'll see if I can pick that back up. It's been doing that lately. It's really annoying. I even restarted everything. I don't know. I guess we're back. It's good. Okay. Hey, what's going on here? There. So the overlap of these, right? X has to be greater than or equal to 2, and x has to be greater than or equal to 6. So now, well, the x greater than or equal to 6 is going to overpower the x has to be greater than or equal to 2. So therefore, the overall domain is x has to be greater than or equal to 6. Finally, we're going to do g of x. So d is g of x. G of x was 2x minus 4, so 2 times g of x minus 4. So 2 times 2x minus 4 minus 4. What's nice is there's no restrictions on g of x, and again, there's no restrictions on g of x. And so here, the domain is going to be all real numbers. I can simplify this a little bit, right? I've got 4x minus 8 minus 4, putting me at 4x minus 12. And the domain here, x is in the set of real numbers. Okay. Working with these a little bit, we can evaluate these functions, right? Because now we've created new functions that we can use and we can find the outputs of. And so if I ask you to find f of 11, in fact, I'm going to put it over here. Well, f of x is the root of x minus 2 and then minus 2. So the root of x minus 2 and then minus 2. So if we plug in x equals 11 here, we get the root of 11 minus 2 minus 2, putting me at 11 minus 2. Don't know, my computer's doing something weird. It's verifying something, okay. Oh yeah, 11 minus 2 puts me at 9, right? So I've got the root of 9 minus 2. The root of 9 is 3. So I've got the root of 3 minus 2. 3 minus 2 is 1. So I've got the root of 1, which is just 1. Okay. What if I wanted to find g of 11? G of g is 4x minus 12. So I've got 4x minus 12, which is 4 times 11 minus 12. 4 times 11 is 44, minus 12, putting me at 32. Okay. Like I said earlier, we can do combinations of more than just 2 functions. Okay, so we're going to see a quick example, and where that's useful is if we have to kind of pick apart a large function and see if we can break it down into 2 or 3 functions instead. That's going to be really useful if you keep going in calculus, for example, right? So to be able to identify smaller functions within a larger function is really useful. So we can also do combinations with more than 2 functions. So if we call it an example, let f of x be, what are we, x to the fourth. G of x is going to be the root of x plus 2, and h of x is going to be, oh, that root looks weird. H of x is going to be 3x plus 4. So we're going to find f of g of h of x, and bracket, and bracket, and bracket. Make sure all your brackets line up. We're not going to deal with the domain here. What a mess, right? But the domain, we can look at these domains individually, right? I can put in any value into h of x, so it has the domain of real numbers. Here, x has to be larger than -2, greater than or equal to -2. And here I can plug in any value for x to the power of 4 and still get a result. So all real numbers, x greater than or equal to -2, and then all real numbers. But like I said, we're not going to go that far. We just need to be able to stuff these things inside each other. So h of x is going into g of x, and then f of x. So what we can do is, I guess I kind of default to starting inside, even though earlier I was stuffing h of x into here. So I'll keep doing the same thing that I was doing. Let's start with f of x on the outside. So inside f of x, I'm putting in g of h of x. So in brackets, I'm going to put g of h of x to the power of 4. Right? This is f of x, x to the power of 4, and inside I've got g of h of x. Okay. Now I'm going to peel back the onion here. So g of x is the root of x minus 2. Notice that it stays inside these brackets to the power of 4, right? So everything is going to happen inside these brackets now. And so we've got the bracket and the root of h of x plus 2 to the power of 4, right? Because g of x is the root of x plus 2, and so, but the x in g of x is going to be h of x, so the root of h of x plus 2, and then I can replace the h of x with 3x plus 4. So I have the root to the power of 4, and h of x is 3x plus 4, and then plus 2. Notice again, I'm putting brackets around, wait, sorry, David, I missed your comment, making it less painful. Without doing the domains, I think.
It's, I was just noting that, hey, it's a square root that's by a positive exponent. Hey, that's
exactly.
Just...
Yeah, it's like, oh, okay, that's
that
gonna
nasty
be
little
fine.
radical goes away.
Totally. Yeah, and good eye. Yeah, because this square root is all to the power of 1/2. 4 times 1/2. Now we're just squaring. Keeping the 3x plus 4 all as one piece, right? Until you can be sure to remove the brackets safely. So now we've got, I'll keep this root here, 3x plus 4 plus 2, being really careful before I start kind of combining things here. So now I've got the root of 3x plus 6 to the power of 4, okay? And I am going to show what happens here. So I've got 3x plus 6 to the power of 1/2. That's making the square root. And then I'm going to put brackets around there again to the power of 4. But notice when we have these exponents, right? We've talked about exponents, or you have with Shaun, we can just multiply these, right? So 4 over 2 is my new power. So I get 3x plus 6 to the power of 4 divided by 2. really kind of writing out every single step here. You can probably skip a few of these, but I just want you to see where it came from. So we get 3x plus 6 to the power of 2. And then we're done. So we can also we can work backwards. I'll put work backwards in kind of air quotes here. We can work backwards to kind of break down larger functions. To break down larger functions. For example, find functions f of x and g of x, okay, such that f of g of x is 5 times the root of 5x to the 3 plus 3. Oops, that doesn't look like 3. Plus 2. Okay. So now remember, g of x has to go in and replace x in f of x. And so there are a lot of different ways that we can do this, right? You might see g of x as 5x to the 3 plus 3, making f of x 5 times the root of x plus 2, right? Or g of x could be the root of 5x to the 3 plus 3, right? And so then f of x would be 5x plus 2. So it just depends on what you pick as your g of x. But hopefully you'll kind of see something, right? You can pull out a whole function here and call it g of x. If g of x is going to be equal to 5x to the 3 plus 3, then f of x must be 5 times the root of x plus 2. And you know what? I'll give you the other option too. Or if g of x is the root of 5x to the 3 plus 3, then f of x is 5x plus 2. It just depends on what you make g of x. How about if f of g of x is 4 divided by x to the 4 minus 6. Now it's going to be more obvious which one has to be the g of x and which one has to be the f of x, right? Because if I make g of x be x to the 4 minus 6, then of course f of x is 4 over x. Let g of x be x to the 4 minus 6, then f of x must be 4 over x, right? And so here, oh yeah, go ahead.
Is another possibility for this f, or 4 over x4 minus 6, would another possibility be 4x squared with g of x being, I don't know, like a difference of squares? Or no,
Yeah.
wait, no, 6 does not really.
I would probably
Okay,
err on the lazy side.
fair enough.
but yeah, so there are a lot of wild, crazy things that we could. And sometimes, so here we don't have any context. We don't necessarily want to pull out x to the 4 minus 6. But what happens later is you might want to pull out x to the 4 minus 6. Or maybe you just want to pull out an x to the 4.
Okay.
right? So maybe you want to make g of x be x to the 4 and then have 4 over x minus 6 as your f of x.
Okay.
It kind of depends on the situation, but yeah,
That,
so you can get as hard on yourself as you want.
okay. I'll try to keep that in mind and not overthink things.
Yeah, I would usually just err on the side of being lazy. Uh, okay, so I think, yeah, we've got a couple more minutes, so that's good. Hey, it's Friday the 13th today. Well, it's been a good day so far. We'll
I don't know.
see.
There's a ton of snow coming down and outside my window, so
Oh, yeah, see, so I'm in Edmonton, and
mm,
we've had snow for a while.
yeah. I was out there for a bit.
Oh, really? Yeah.
Will do. It's a nice community.
Yeah. But it's nice and bright. So driving sucks though. Okay, so section 2.8 is the last section in chapter 2, so that's nice. It's on one-to-one function and their inverses. So inverses of functions kind of undo a function. So it's not necessarily just 1 over x, it's going to be a little bit more complicated than that. So one-to-one functions, one-to-one functions and their inverses. Okay. So the first thing is, in order for a function to be invertible, it has to be one-to-one. And that's a pretty common kind of concept checking question that you'll be asked. So in order for a function to be invertible, oops, it must be one-to-one. One-to-one. Okay, so one-to-one means that each input only gives you one output. And also, every output is unique to one input, right? And so to be a function, it has to, so we have to have an x and it has to map to a unique output. Okay, let's see here. Recall, let's start there. A function can only yield one output for each input. A function can only yield one output for each input, right? Every x only yields one y. Every x only yields one y. Okay. So we can check that using the vertical line test, right? We can check this, check for a function using the vertical line test. Okay. So that means that something like this, x squared, for example, right? X squared is a function, okay? But what we'll see is that x squared is not one-to-one. So here, every input gives one output, right? And I'll do my little vertical lines here, right? We only cross at one point. That's a function, okay? One-to-one 1-to-1 adds the condition, so we have to have a function. So for a function to be 1-to-1, for a function to be 1-to-1, each output can only be generated once, right? And so here, notice that if I plug in x equals 2, I get the same output as I do when I plug in x equals -2, okay? And so what happens is if we have kind of x equals 2 and x equals -2 up here, sorry, I kind of crowded this, they yield the same output, right? And so here, for a function to be 1-to-1, every output must map to a unique input, right? So every x, or sorry, every y must come from a unique x. So in this case, right, x squared then is not 1-to-1 because here I've got a y value of 4, right? But I can map it back to x equals -2 and x equals 2. So it's not 1-to-1. Okay. So we can check this. We can check if a function is 1-to-1 graphically by using the horizontal line test. So we do the same thing that we did for functions, just horizontally now, right? Because what I need to do is I need to make sure that if I draw horizontal lines instead, then I can only cross this graph once. Right here, I'm crossing it twice, so it's not 1-to-1, which we just established here. By using the horizontal line test. So for example here, like we said, x squared, for example, if I draw horizontal lines across here and here, so therefore it's not 1-to-1. Yeah. Whereas if I have something like, I don't know, let's say I've got something like this. What did I want to use? Like that, right? We haven't talked about exponential functions, but just kind of imagine, in fact, I'm going to remove this and make it any even power of x. Here, if we've got this type of scenario, then if I'm drawing horizontal, well, if I draw it first, let's check, make sure it's a function. Yes, it's a function because I can cross this and I only cross the graph once. And here, I can cross it horizontally and only intersect the curve one time, right? And it maps back to a unique value of x. And so therefore it is 1-to-1. All right, so I know I'm out of time here. Next day, I'll show you how to, so this is how we check for a 1-to-1 function graphically. So if you have a graph, or if you have an idea of what the graph looks like, that's useful. But we can also check it algebraically, right? So using math, and it's a little bit more of a rigorous statement. Okay, it's 1-to-1 because I was able to show this. So that's where we're headed next day. Any questions?
I don't have any. I don't know about
No?
the others.
Then I hope you have a really great weekend.
You too. Ciao, ciao.
See ya.